So now that we have the definition, let's go through an example where we use that to evaluate a definite integral. So you see here that we have the specific function is 5x plus 3, and a is 2 and b is 6. So let's just kind of formalize that here. So this tells me what f of x is, this tells me what a is, and this tells me what b is. Okay, so the other thing that's worth pointing out here is that I have a sum formula provided. So that's not something that's supposed to be obvious, but we'll see that once we go through this process, there's going to be a point at which I need to know the sum of k from k equals 1 to n. So to start with, I want to think about exactly what the definition requires. So needing the definition, we need to express this integral as the limit as n approaches infinity of the sum from k equals 1 to n of f of xk star delta x. Okay, so let's find some of the necessary pieces. First of all, I like to start with delta x. So in this instance, notice that we're looking at a Riemann sum with n rectangles, so we don't have a fixed value for n. So if I know that my interval is from 2 to 6 and I have n rectangles, we define delta x to be the length of the interval divided by n. So in this case, delta x is going to be 4 over n. Once I have delta x, then x sub k is a plus k delta x. We just said a is 2 from looking at the integral, and k times delta x is k times 4 over n. So xk is 2 plus 4k over n. Now, for f of xk star, remember that that is representative of infinitely many choices that we get to make. And when I send n to infinity, the choice we make doesn't matter because all of these things converge to the definite integral. So that means that I get to choose whichever type of Riemann sum I might like. So I'm going to just let xk star here be exactly what xk is. So effectively, when I'm going through this, I'm looking at a right-hand sum, which is an arbitrary choice. And in fact, it doesn't matter that I made that arbitrary choice when I send n to infinity. Okay, so the next thing I want to consider is the terms of the sum. So let's think about what f of xk star, or in this case xk, delta x looks like. So f of xk delta x is equal to f of 2 plus 4k over n times delta x is 4 over n. And here I'm coming back up to what I have in pink. The function f of x is 5x plus 3. So if I were to replace x with 2 plus 4k over n, I'm going to get 5 times the quantity 2 plus 4k over n plus 3 times my delta x again, 4 over n. And I just want to simplify this as best I can. So first of all, distributing the 5, I'm going to get 10 plus 20k over n. I still have the plus 3 in there. And this is all multiplied by 4 over n. So notice that the 10 plus 3, that's going to be 13. And we can then distribute 4 over n. So I'm going to get 4 times 20, so 80k over n squared. And then the 4 times 13 is 52, and that is likewise over n. So this is what this part that I've boxed up here can be replaced with. So at this point, I can say that the integral I'm trying to evaluate, the integral from 2 to 6 of 5x plus 3 is equal to, the limit as n approaches infinity, of the sum from k equals 1 to n of what I found in the previous line. So 80k over n squared plus 52 over n. So what I'd like to pause here and point out is that when I'm going through these problems, my approach is to simplify what I'm going to box in blue here as much as possible to the point where I can get rid of the sigma notation. So I'm going to hold off on the limit. And then my very last step is going to be to take the limit as n goes to infinity. And you'll note that once I simplify what I have in blue and I no longer have the sigma notation, the task of taking the limit is no longer going to be complicated. So the other thing, let's come back up and use a different color here. I know that this formula is probably going to come in handy somewhere. And notice that involves the sum of just k. So what I'm really focused on in my part here is that I have the sum of k, but I have some other things involved with that. So what I'm going to rely on now is something we talked about with the properties of sigma notation. So for one, because I have the sum of two things being added together, we saw from our sigma notation properties that I can split this up. So taking the limit of both things, but I can write this as the sum of just 80k over n squared plus the sum of 52 over n. So that's one thing I can do. And then the other thing I can do with the goal of trying to bring in the sum of k, which I have here, is we saw that we can bring constants, multiplicative constants, outside of sigma notation. So 80 over n squared is constant with respect to the index k. So notice I can't bring that outside of the limit. It depends on n. But I can take this part and just bring it out here. That was another property we saw of sigma notation. So this is also equivalent to then 80 over n squared, the sum from k equals 1 to n of k, plus the second part. And as we become more comfortable with doing these processes, I could have combined these last two steps into one. But notice what's really special now is I have this sum that I've boxed in green, and that's exactly the given sum that we have in the problem. So I'm going to be able to replace that sum that I boxed with n over n plus 1, n times n plus 1 over 2. So that's one way to get rid of sigma notation. So in this next step, I'm going to take advantage of the given formula, which allows me to write this first part as 80 over n squared, and I'm replacing the boxed sum with its equivalent n times n plus 1 over 2. And then how to get rid of the second one. So we aren't given a formula here, but I want to point out that what we're doing is we're adding a constant again and again and again. So when k is 1, the term of that sum is 52 over n. When k is 2, the term is 52 over n, etc. So in general, if we have a constant, so let me just put this over here. Let's just call it c. In this case, c is 52 over n. That's saying what's c plus c plus c, etc. And then we know that there are n terms here. So I'm adding c to itself n times. That's just going to be c times n. So think about if you add 10 to itself 5 times. We would say that that's 10 times 5. Same idea here. So this is just going to be a useful thing to remember for constants. And again, by constant, I just mean constant with respect to the index of our sum. So in this case, we're going to take the constant 52 over n multiplied by the number of times we're adding it to itself, which is just n. So here we've arrived at the desired step where we've simplified the sigma notation. We no longer have a sigma notation in there. And here I'm just taking the limit. So yes, you could multiply this out. You could also use L'Hopital's rule, but we don't need to because, again, with my limit properties here, I can see that the limit is going to look at, first of all, the first part, you're going to have a second degree polynomial divided by a second degree polynomial. So we can take simply the leading coefficients, 80 over 2. And in this second part, I can cancel the n from the top and the bottom, and that's going to just be 52. So we get 40 plus 52, or we get 92. And again, like I said, you could kind of go a longer route to getting that limit, but you can take advantage of the fact that you have these equal degree polynomials in the numerator and the denominator to get there more quickly. Later, we'll also see another way we can much more rapidly get to this final answer of 92. But in the instance that we're prompted to do so using the definition, even if we have other tools at our disposal, we want to make sure that we know how to go about using the definition to get that final answer.